The mechanical engineering bottleneck for robotics has shifted from raw compute speed to a physical latency problem that no amount of clock frequency can solve. Current silicon architectures suffer an 8 order of magnitude efficiency gap compared to the human brain, creating a memory wall that prevents real-time physical decision-making in compact form factors. This video unpacks how sequentially stacking silicon changes the game by co-locating memory and processing, turning theoretical speed into actual autonomous capability. For decades, the narrative of Moore's law focused on squeezing more transistors onto flat wafers to boost raw performance. But for a robot navigating a dynamic environment, that approach is hitting a hard physical limit. The issue is not how fast the processor can think, it is how long it takes to fetch data from memory and return results. In traditional von Neumann architectures, logic units sit far away from storage units, forcing billions of bits to travel back and forth across copper interconnects for every single calculation. This movement consumes massive amounts of energy and introduces latency that scales linearly with distance. For a humanoid robot or an autonomous vehicle, this delay is the difference between catching a falling object and watching it shatter on the floor. The physical act of moving data creates a bottleneck where the processor spends more time waiting for information than processing it, rendering high-speed calculations useless when milliseconds matter. The solution lies in abandoning flat designs entirely to build vertically stacked silicon systems that mimic the brain's density. By stacking layers of memory directly atop logic circuits using advanced through-silicon vias, engineers can eliminate the long copper highways that cause delay. This architecture enables a massive jump in bandwidth while drastically reducing power consumption because data travels only microns instead of millimeters. The result is a system where sensor fusion, the process of combining inputs from cameras, LiDAR, and inertial measurement units, happens at speeds previously thought impossible for general-purpose chips. Instead of waiting seconds or milliseconds to aggregate environmental data before acting, the robot can now fuse sensory streams in microseconds, allowing it to react to physical dynamics as they unfold rather than processing them after the fact. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This shift from continuous signal processing to sparse binary spike events fundamentally changes how machines learn and decide. Traditional deep learning models on GPUs consume massive power because they process every pixel and every frame continuously, regardless of whether anything has changed in the scene. In contrast, neuromorphic stacked chips operate on a spiking neural network paradigm that mimics biological neurons firing only when necessary. This approach allows deep reinforcement learning to run with energy efficiency measured in microjoules, rather than the picojoule requirements of traditional architectures for similar tasks. The system becomes event-driven, reacting instantly to changes in the environment while remaining dormant during periods of stability, mirroring how a human nervous system conserves energy by ignoring constant background noise and focusing only on significant stimuli. The practical impact of this architecture is already visible in hardware-embedded systems that achieve deterministic responses previously unattainable with standard CPUs or GPUs. FPGA prototype chips embedding ROS2 infrastructure have demonstrated latency reductions to just 11 microseconds, a figure that mirrors the firing times of biological neurons, which range between 2 and 5 milliseconds. This level of determinism solves the jitter problem inherent in traditional operating systems where background tasks can unpredictably delay critical sensor inputs. By hardwiring message-passing protocols into the silicon stack itself, these chips guarantee isochronous responses within 1 microsecond, ensuring that a robot's reaction time remains bounded and predictable even under heavy computational load. However, moving from theoretical benchmarks to mass deployment introduces significant engineering trade-offs that challenge traditional software development workflows. The transition from general-purpose computing to specialized, deterministic circuitry replaces the flexibility of whack-a-mole tuning with rigid hardware constraints. While a standard CPU can be reprogrammed instantly via code updates, neuromorphic stacks often require specific physical configurations tailored to their intended tasks, making them less adaptable but infinitely more efficient for those specific applications. Current adoption is limited primarily to FPGA prototypes and specialized test beds rather than the mass-produced silicon found in consumer electronics or industrial robots. The ecosystem required to universally adopt this architecture remains nascent, lacking standardized, off-the-shelf components that allow engineers to simply plug a neuromorphic stack into any robot design without extensive custom integration work. Despite these hurdles, the trajectory points toward a future where autonomy is defined not by clock speed but by physical proximity of computation and memory. As stacking technologies mature from laboratory proofs of concept to industrial manufacturing standards, the power-to-compute ratio will continue to improve, enabling robots that can operate for days on a single charge while processing complex sensory data in real time. This engineering reality moves us beyond the hype of faster processors toward a new era where machines possess the mechanical intelligence to interact with the physical world as fluidly and efficiently as biological organisms do. The memory wall is not just being broken, it is being dismantled layer by layer, paving the way for autonomous systems that can finally think fast enough to keep up with reality. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.